Hello and welcome to part 6 of this series of videos about denotational design on affine functions. So in this video, it's very much unscripted. I'm going to just prove that the operations plus circle and 0if form a monoid on the representation. Now we know that they form a monoid on functions. That's a standard result which is well known in the mathematical community, and you can prove it in AGDA, but I won't be doing that. So I'm now going to show that this is a monoid as well. Let me just take you through what I've done here. As usual, I've put everything inside a submodule so that there's no conflicts with the rest of the module. I've imported relation.binary.propositional equality, which is what introduces this operator here, which is defined with just one constructor, refl, which says that x is equivalent to x. So it's actually only true when the things are actually identical. Okay. And then I've imported both algebra.definitions and algebra.structures, and these are interesting modules in that they are parameterized. So I've actually passed in q cross q as the type, and I've passed in propositional equality as the equivalence relation, so that we will actually be doing proofs on that data structure and that equivalence relation. Then I've written down the definitions of plus circle and 0if, and I've also imported relation.binary.bundles, which just has some helper stuff in it. And then what I'm going to do is prove that plus circle and 0if form a monoid. So let's have a look at what this is monoid record looks like. So I'm going to hit meta dot, increase the size of that, and I'm going to have a look at is monoid. So it takes an op2, which is A to A to A, as you can see, and it takes an identity element of A, and then it has two fields in it, is semigroup and identity. Now we'll look at identity first. If we look at this here, it says that you can think of this as a type synonym. Identity E dot is a product of left identity E dot and right identity E dot. Left identity is this property that for all x E dot x is equivalent to x, and right identity is for all x x dot E is equivalent to x. Okay, so to fill in this particular proof, you have to have a proof for left and right identity, and then you put one as the first component of the pair and one as the second component of the pair. The next thing is, the next field is semigroup. So is semigroup has a field is magma, which we're not going to worry about at all. It turns out that I think everything's a magma under propositional equality. But we are going to worry about this associative operator, and that simply says that for all x, y, z, brackets x dot y dot z is equivalent to x dot brackets y dot z. And we're just going to fill in the proofs for identity L, identity R, and a sock. That's what we're going to do today. And as you can see, I've left holes. So this whole thing type checks with holes. So it's not complete yet. It ain't over until there's no holes left. So why don't we start with one of the easier proofs first, which is simply identity L, okay? I'm going to work forwards here, and what is 0AF equal to? Well, it's equal to 0Q, 0Q, circle plus F, and you know what? I'm going to pattern match on F this way, so that allows me to write this here. Control C, Control L. That's gone through, and now we can apply the definition And that's going to be 0q plus f1, comma, 0q plus f2. And that's that hasn't gone through for some reason. And I wonder why. I'm wondering whether I need to simply bracket those things. That's possible. No. Okay. I can't work out why that's not going through. All right, well, let's just take a look at the definition of plus again. Plus circle. Or circle plus, as I've been calling it. Ah, okay. Well, I've made a huge mistake here. So I actually got the definition of this wrong. So that should be f1 plus g sub 1, and this one should be f sub 2 plus g sub 2. That's the actual definition that we derived in the other video. And I've just written this out thinking I could get it right from memory, and got it wrong. And well, this is great because it's showing you that showing you the value of AGDA, in that wasn't going through when it clearly should have, because the definition was wrong. So if I reload now, that's gone through. Great. Okay. So now we can see that we're pretty close to where we want to go. I might just go backwards from here and expand f out to be f sub 1, f sub 1, f sub 2. Reload. And then what we want to do is use the left additive identity law twice on a pair. And for this, I'm actually going to use something called Cong2. Okay, I just want to show you what this is all about. So Cong2 is something you get for free with propositional equality. I mean, there's a library for it. And it says that if x is equivalent to y and u is equivalent to v, then f of xu is equivalent to f of yv for all f. In this case, our f is actually going to be the pairing comma. Okay, that the actual function that takes two things and gives you back the pair. So it goes from a to b to a cross b. So I'm going to put that in, because that is a function. It's actually a constructor. And now you can see over in our goals that we've simply got to show that 0q plus f1 is equivalent to f1 and 0q plus f2 is equivalent to f2. And that's actually just additive identity on the left-hand side applied to f1. Great. And then we can do the same thing over here, except applied to f2 and refine that. Oh, it's got an extra set of brackets, so I'll just remove those so it looks a bit nicer. Yeah, okay, so that proof's gone through. The one on the right is going to be almost exactly the same, so actually I'm probably just going to copy and paste. Well, let's copy and paste the middle of it and then do a bit of a reshuffle. So we have f circle plus 0f is that, and then that's going to be that, and then instead of left identity, we're going to be using right identity. Nearly. Oh. I missed that. Okay, there's our second proof. So we've proven the left identity and the right identity, and that's filled in up here. So we've done that. And there's only one thing that remains, and that is associativity. So let's get started on that. So the first thing I'll want to do is work forward and expand out this definition. So that's going to involve me pattern matching on each one of these things. And then I'm going to want to simply expand this out. We'll load that and see if it works. That's worked really nicely. And I might just go ahead a few steps. ACT is actually quite smart at doing some normalization. So what I'm going to do is I'm going to write out what I think this will eventually evaluate to. And I think it's going to evaluate to this, H sub 1, and then F sub 2 plus G sub 2 plus H sub 2. I could have done more steps there, but I think that's what it's going to evaluate to, and great, AGDA agrees. And also, if we were to work backwards, then I would say this expression at the end evaluates to that. So let's see if that goes through. And so now we have the situation where we want to show that this is equal to this, and again I'm going to use Cong2, and I'm going to use the pair operator, and I'm going to use plus a sock and plus a sock, and I might just put that on the next line, and then we're just going to fill this in with the right arguments. So it's plus a sock on F1 G1 and H1 and F2 G2 and H2. And there you go. We've proven associativity. And now we can safely say that we have a monoid under circle plus and 0AF. But here's the interesting thing. We didn't actually need to do this. So it's very nice that this is true, but we didn't actually need to do it. And I'm going to show you why this isn't true in the next video. In fact, I mentioned it in the introduction video. So because we know that affine functions under addition and the constant function that returns 0 are a monoid, and we've defined the meaning function in such a way that there's a monoid homomorphism between this representation and the denotation, then the laws transfer from the denotation to the representation. So that's what I'm going to show you in the next video. It's going to be a long one. So see you in the next video.